Okay, Algebra 2, Unit 2, Lesson 1 is called Let's Make a Box. All right, so our learning goal today is I can write and interpret a polynomial that models the volume of a box that is created by cutting squares out of the corner of a sheet of paper. So basically what is going to happen here is we're going to have a sheet of paper here, and the dimensions on the sheet of paper don't really matter. Let's say I'm just going to use whole numbers here. I'm going to say this side is 10. And let's say this side is, 15. So if I cut squares out, all right, and I call these x, that would mean they all have a length of x. We're going to basically cut these out. So we're going to, rip those out, and we're going to make a box by folding these dotted lines up. Okay, we're going to fold these sides up, fold all these sides up, and tape it all together, and it'll form a box. So we're going to be able to come up with a polynomial from that situation. All right, so moving on. So first of all, what is a polynomial? It's part of our learning goal. Polynomial is a function of x. Polynomial function of x is a function given by a sum of terms, each of which is a constant times the whole number power of x. The word polynomial is used to refer both to the function and to the expression defining it. So an example, I call f of x my function, 3x squared plus 2x minus 1. If I got another one, g of x, 4x to the third plus 2x minus 1. All right, those are some examples. Notice you have a constant times x to a power, constant times x to a power, and a constant. Really, it's times x to the 0, but we don't need to put the times x to the 0, but it's there. All right, so that's a polynomial there. Notice you don't have negative exponents. Notice you don't have fraction exponents. And you add up all the terms. All right, so let's start with our warm-up. Which one doesn't belong? So I'm trying to come up with a reason for all of them. A would be obvious because A does not have a picture. So if you pick A, we'd say that's because there's no picture. If you check the volume on all of them, it's length times width times height. So if you go ahead and multiply them all out, let's see here, 4 times 8 times 10. This one has a volume of 320. This one would be 10 times 2 times 8. This volume equals 160 cubic centimeters. This one here is 320 as well. And then this one, they tell you the volume, so I can't really multiply it out because I don't have numbers there. But right away, I could say B is the only one with volume not equal to 320 cubic centimeters. If I go to C, you could probably say, since this one's, oh, you know what? I was wrong here. That's not centimeters, that's inches, cubic inches. So right away there on that one, you could say, oh, C is the only one in inches. And then this one, you could say it's the only one with variables for the sides. Now, luckily, we only have one variable. The only variable there is x. Now, this is 4x, and then this one here is x, and then this one's x plus 1. But luckily, we don't have x, y, z. We don't have multiple variables, so that's kind of nice. All right, so on to the first activity. So if you were here in class, we would be doing this with like a piece of paper and scissors and a ruler and stuff like that. But I'm going to try my best to do it here without that. So, um, so basically, we're going to construct an open top box from a sheet of paper by cutting out a square from each corner and then folding up the sides. So on a standard sheet of paper, this side is 8.5 inches, and this side here is 11 inches. Okay, so if you were in class, I'd be giving you a sheet of paper that was 8.5 by 11. And what we're going to do is we're going to cut out squares in the corner. Okay, so I'm going to make a little square there. I'll tell you what I'm doing. Copy. Paste. That would be the same. What's that other? Paste it. Oh, here it is. It's all over here. So I cut these squares out. And basically, we're going to start with a side length of 1. If you look right there, it says 1 to start. So I'm going to basically label this as 1 by 1. All right, so what happens is when I go to make this box, you're going to cut out those corners, and these dotted lines are going to be the folding lines, and these pieces right here are going to all get folded up. So I'll use some colors here. These get folded up. These get folded up. Okay, and then the little squares that we drew get thrown out. So if we get a box down here that looks like this, okay. So what happens is when you fold it up, if you look here, this side right here is going to go with that. So what is that side? Well, it was 11 to start, but you're taking off 1 and 1, so this side's going to have a length of 9. Okay, and then this side over here, all right, this side had a length of 8.5, but you're cutting out 1 and 1, so this side's going to be 6.5 right there. And then if you look at the height, when I fold this flap up, really you fold all these flaps up here. Okay, when you fold them up, that's going to have a height of 1. So what's the length, the width, the height? So length will be 9, the width will be 6.5, and the height will be 1. So what will be the volume? We got to multiply those together. 9 times 6.5 times 1, that's 58.5. So I'm going to just change it. I'm going to make this a 2. All right, so all I'm going to do here is I'm going to just change these numbers here to 2. I'm not going to redraw the picture. I'm just going to change the numbers, and we can kind of mentally just do it. So if these are 2 by 2 boxes, remember this was 11 right here, okay? So I'm subtracting 2 on the top and 2 on the bottom. So that blue side there is now going to be 11 minus 2 minus 2, so that's going to be 7. The green side right here is going to be 8.5 minus 2 minus 2. So 8.5 minus 4 is 4.5. And then when you fold up the flap, that's going to be 2 now, right there. So I can fill everything in here. Height is 2. I should use blue. There we go. Length is 7. This is 4.5. So let's multiply those together for volume. Length times width times height. 2 times 7 times 4.5 gives me 63. And let's go ahead, let's try 3. So I'm going to just change these 2's to 3. So these little flaps are 3 now. Fold them up. This side here with the blue, this side of the box now becomes 11 minus 3 minus 3. 11 minus 6 would be 5. The green side over here was 8.5 up top. So the bottom is 8.5 as well. 8.5 minus 3 minus 3, because it's really, the whole thing's 8.5 all the way across, but you're basically, this is 8.5 right here. It's like you cut off this piece, which is 3, and this piece, which is 3. So it's like you subtracted 6. So that would be 2.5. And then your flap that you fold up would be 3. Oops. Oh, that can be right. So your volume is going to be length times width times height. So go ahead and multiply those. Gives me 37.5, okay? So if you kind of plot those, if you look here, side length of the cutout, we got 1 has a volume of 58.5, 2 has a volume of 63, and 3 has a volume of 37.5. So it looks something like that. Okay, now, if we were in class, we might do some more numbers. I could give different groups different sizes, but basically what's happening is you get a shape somewhat like that. Okay, so the key is, since volume is on the y-axis, we want the maximum volume. So the maximum volume is going to be right around at that point, which would have a side cut out of like 1.75 roughly. All right. All right, so the volume v of x in cubic inches of an open top box is a function of the side length x inches in inches of the square cutouts. Make a plan to figure out how to construct the box with the largest volume. Okay, so basically what happens here is, what you need to know is you need to know the lengths of the sheet of paper. So we're going to keep the same numbers. We're going to go 8.5 by 11. And when you start cutting these squares out here of the corners, we could just call these x. X by x, x by x, x by x, okay? And what happens is the volume, when you make your box, your volume, it's always going to be, the side that's 11 over here, this is going to be 11 minus 2 x's, because it's like you cut these x's off and got rid of them. The bottom side is going to be 8.5, but then you're minusing 2x because you get rid of 2 of them. And then when you always fold up the flap is always going to be x. So I guess I kind of did 1 and 2 together. And it'll always kind of be the same exact thing anytime you go to make a box. So, let's just, for the heck of it, let's say that I had different sides here. Okay, let's say that this paper was different dimensions. Let's say this side was 20 and this side was 15. If that was the case, your volume, v of x, is going to be 20 minus 2x. 15 minus 2x times x. It's pretty much always going to follow that pattern with a sheet of paper, or a sheet of cardboard, or whatever. Okay. All right, let's go on to the third question. Use graphing technology to create a graph representing v of x. So I went back to the original numbers, 11 and the 8.5. All right. Approximate the value of x that would allow you to construct an open top box with the largest value. So we want to find the part on the graph that is a maximum. So I plotted my function that I had on Desmos, and my maximum is right here, that point. So this axis is volume, and this is, this is side length of a square. Okay, so obviously my maximum volume is 66, and the side length that would work for us would be 1.585. All right, so you're looking for that maximum. Why did I pick that point? Because it's right at the top. You see, we go up and then we come down. That's a max. All right. Now you might say, well, it goes higher up here. It does, but 6 inches is too big of a square to cut out. You won't have enough paper left over to make a box when you fold it up. All right. So what strategy did you use to answer the question? I would say we drew a picture. Label. Use knowledge about volume. Right. What are some side lengths for the square cutouts that don't make sense? So that was kind of what I was talking about earlier. So you got your picture here, and basically, whoops, this side's 8.5, this side's 11. I can't go over half of the smallest side, because look, what's 8.5 divided by 2? 8.5 divided by 2 is that 4.25. I can't make a square that's bigger than 4.25 because, if my square here is 4.25 and I cut them, there's not going to be any box left to fold up. It's going to basically, I'm going to cut it into right here. I'm going to cut it right there, and there won't be a side left on that piece to make a box. So basically, your smallest side should say, we can only use less than half of the small side, okay? Because we just won't have any left to make a box. Now, if this was 4, this is 8.5. Oops. If I made these a little smaller, if I made these, 4 and 4, we would have, right here, we'd have 0.5 left, because if you add up all those sides, if you add up this plus that, it'd be 8.5. But you got to have less than half of the small side. Okay. All right. Let's take a look at this one. Outside the United States, the common paper size is called A4. It measures 21 by 29.7 centimeters. Let V of x equal 21 minus 2x, 29.7 minus 2x, and x, or times 21 minus 2x times 29.7 minus 2x times x. Be the volume in cubic centimeters of the box made from A4 paper by cutting out squares of side length x in centimeters from each corner and then fully emphasized. What is the reasonable domain? So the smallest side here, so this is kind of the same thing that we just did. The smallest side would be 21, whereas the longer side would be 29.7. So half of the smallest side, so you could say here, small side equals 21 inches, long side equals 29.7 inches. So half of the smallest side would be 10.5. So we can only cut squares less than 10.5 inches in length. Okay, it's got to be half of the smallest side or less. All right. So, let's do one more thing just to make sure we got this. So if I give you my sheet of paper, it looks like this. I'm going to make up some random numbers here. Let's say this side is 32 inches. And let's say this side is 18 inches. So you cut out your boxes, x by x, x by x, x by x, x by x. So your volume function is going to be 32 minus 2x times 18 minus 2x times x. All right, it's always going to be each side length minus 2x and then times x for the height. So your domain, so take your smaller side, which is 18. So x has to be less than half of that, so less than 9. Okay, 18 divided by 2 is 9. So your side lengths have to be smaller than 9. All right. So there you go. Hope you enjoyed the lesson.